Good. Okay, so I think we can get started. No one wanted to introduce me. Although I think you know who I am by now, especially the folks in remote sensing. But I'll just do a quick introduction. My name is Jan van Aardt. I'm from South Africa originally. I studied forestry and then fell in love with remote sensing through a mentor of mine who was a physicist, a literal rocket scientist, Ben Opperman, and he introduced me to the physics of remote sensing. And me being from biology, I fell in love with that interaction between biology and physics, and now it's captured in remote sensing and imaging science by some extent. And I thought I'd talk today about a little bit of some of what happened since I started at RIT. So I'm leaving quite a few of the student rock stars out of this who've done other research, like Amir has worked on precision agriculture. Rob Chancia has done that too. He's a postdoc now here. But I really owe a lot of what has happened over the 15 years at RIT to the folks on this line. And I mean it sincerely, I'm not exaggerating. I was driving back home from a trip in South Africa once. I landed at Oliver Tambo International Airport in Johannesburg, and I was driving back to Pretoria, and the equivalent of sort of a national public radio was on, and I was listening to an interview with someone, I think he was some famous hedge fund manager or bank manager or someone retiring. I don't even know who it was. And they were asking him, what did he attribute his success to? And he said he always surrounded himself with people that are better than him. I thought, wow, that's pretty cool if you can do that, right? And as things have played out, I've been surrounded by people that are better than me in when it comes to this kind of science stuff. So I can sort of ride their coattails, and I mean it sincerely. They've been amazing students. This program has been amazing to me, and there's been some cool science. So I thought today, why is this not going? Let's see. There we go. I'll sort of tell you a little bit about what I've done in terms of forestry remote sensing, but specifically LiDAR. It's been a riot. I came to RIT as an empiricist. I'm a forester who likes to measure things. I really like to measure trees, whether it's the diameter or the height, and then plug it into a model. And then I arrived at RIT in imaging science, and I was exposed to this thing called DIRSIG, digital imaging and remote sensing image generation. It's a simulation environment started here by a guy called John Schott. And I don't know, Carl is not here. I wanted to put up a picture of Carl because he was one of the first coders on DIRSIG. But the picture I had of him was one with a mullet. And I didn't want to do that to Carl. He had this long mullet in the book that John Schott wrote. But I thought that exploring DIRSIG and the simulation environment for science was an interesting challenge. And I've become a convert of that for a variety of reasons that I hope to convince you of. So I'm going to sort of tell you a little bit about forest cartoons, and starting at the very beginning with a student called William Wu. And now we're building more complex and better scenes, all in order to exploit what happens when laser signals travel through a forest and try and extract forest. We call it biophysical parameters. So anything that has to do with the biology and the physical nature of trees. So just quickly, what is LiDAR? Light detection and ranging. I think most of you are aware what LiDAR is, but I thought I'd just quickly talk about that. It's literally the optical analog of radar, radio detection and ranging. And it's essentially a system that emits very brief pulses, typically 2 nanoseconds to 60 nanoseconds in duration, and very rapidly. Then the new LiDAR systems can pulse 500 kilohertz. So that's 500,000 pulses per second. It's amazing. And then you get this geolocated point cloud that essentially has an X and a Y and a Z, a height coordinate, as well as an intensity measure for that wavelength of LiDAR. You get different flavors of LiDAR when it comes to ranging LiDARs, because there's also atmospheric LiDARs. You get waveform systems on the left here. So as the signal propagates through the atmosphere, interacts with the canopy, you sort of digitizing the entire backscatter as a function of time. So you've got height or range on this y-axis, and then intensity on the x-axis. You can sort of see this cartoon showing what it would look like in a tropical forest. Then you get discrete LiDARs. So they actually measure the discrete detection at a specific point. This is a terrestrial scanning system from Belgium when I was a postdoc there. You can see the stems clearly. But because it's a terrestrial system, similar to the one in the front of the room here, you have very dense point clouds close to the system, and then it sort of occludes, you get occlusion at the top of the canopy. And then the newest flavor when it comes to ranging systems are what's called photon counting LiDARs. And I know Dr. Kerekes has worked on those with a university at Buffalo. And this is sort of an example of a Mabel system. It's an airborne system flown over, I think this is in the Sierra Nevadas in California. And you can sort of see the system literally detects individual photons at a specific wavelength. So there's a lot of atmospheric noise, but you can sort of see the distribution of the topography as it's counting those photons. So these are the three main systems. I mainly work with the leftmost two. So waveform and discrete systems. And I thought I'd show you the beauty of LiDAR. This is from Dr. Crystal Scharf, UMass Boston, La Selva Biological Research Station. So you're looking at terrestrial laser scans, millions of individual colorized points. And you and I can probably easily pick out the structure in there, the ferns, the trees. But I challenge you to come up with an algorithm to detect the ferns, to measure the ferns, to detect the trees, measure the trees. You get where I'm going. It's a really complex data type to analyze because it's not a rasterized product as we are used to in imaging, right? So it becomes a pretty complex problem just by how the data is structured. So just briefly, I love talking about these kinds of things. And I tell the students in one of my classes, you're going to wake up in a cold sweat at 3 a.m. in week 6 of the class because you're going to see this graph right here. But what you're looking at here is on the y-axis reflectance by wavelength. And this sort of bold black curve is a typical reflectance curve for vegetation. Very typical. Some of my students are, yeah, I recognize that immediately. If you click on a pixel in an image and it has this reflectance curve, you say vegetation without hesitation. So in the blue and the red, absorption due to photosynthesis, the chloroplasts absorb light. In the green, the chloroplasts interact a little bit with that green light and backscatter, hence our perception of green leaves, right? And then you've got this very steep increase called the red edge, and then this near-infrared plateau, sort of the near-infrared region right here. And that near-infrared region is due to the internal scattering of photons by the internal scattering in the leaves. And then this short-wave infrared region, you see some water absorption features where the moisture in the vegetation is actually absorbing the energy. But this is a beautiful graph, I think, because on the other axis, it's actually plotting transmission. So why would we use a near-infrared wavelength, which is what we typically use? That's a 905 nanometer laser in the corner, and we typically use 1064. Because look at what happens to near-infrared energy when it hits leaves. It's highly reflected, very little absorbed, and highly transmitted. So I suddenly have a wavelength that can penetrate the foliage, and if you're lucky, to the ground, and backscatter to the detector. There's a limit, though, because in the right graph, again, you see reflectance by wavelength, and this is what we call volume reflectance. So now look at what happens in the infrared as I add leaf layers. Firstly, I get reflectance, and then it's sort of a nonlinear reduction in reflectance as I add leaf layers. So the near-infrared energy is actually dissipating through this mechanism of volume reflectance, because you can think of that bundle of near-infrared photons. Some are reflected, some are transmitted. Next layer, some are reflected, some are transmitted. And you've got scattering in multiple directions. Some are transmitted, some are reflected. And you can ping pong your way through the canopy. And you see by the time you get to quite a lot of leaf layers, you basically have saturation. You don't receive any more near-infrared photons at the detector. So this is important later, but again, near-infrared, really helpful for us to penetrate, transmit through the canopy, versus a green laser that's basically, by majority, photon-wise, absorbed at the first or second layer. You get very little transmission in the green lasers, which is another kind of laser that you fly. We typically fly either 532 nanometers or 1064. Those are the two main wavelengths. I got this graph from Flip Phillips, and he said you can lie with cartoons. And you can see, I think some of you have seen this before in his presentation, but this character, she's doing things that is physically impossible, right? Yet it doesn't disturb us all that much. We're in the moment, if you will, in the scene. And I say that because whenever I go to a NASA meeting or an SF meeting or NGA meeting talking about DeerSig, a lot of the people glaze over because they say, you're just using simulation. You can tweak that simulation to prove whatever you want to. So I think it's really critical that we benchmark it, which the DeerSig team, they're aggressively doing that. There are a bunch of other simulation tools out there internationally, and that we also validate it through our studies. And that's what a lot of what has happened with the DeerSig team too. So what is DeerSig? It's essentially an entire, call it an ecosystem, if you will, where we populate the scene with, I would say, robust geometric models, either ones that we construct or we develop or we beg, borrow, and steal from someone, right? Then we attribute those models with proper spectral and emissive characteristics. We want to know what happens to the photons when they hit a specific object, right? This is all sort of in a big engine. We can parameterize all the collection information, you know, the focal lengths, the optics, the focal plane, the different detectors, the atmosphere, very important. We can add different atmospheres to look at what type of scattering and then absorption happens. And then we can render. Then we can ask interesting questions. What if we cast photons into the scene? It has to travel through, they have to travel through the atmosphere, interact with the target, and we have a specific sensor. Maybe it's LiDAR, maybe it's radar, maybe it's something else, right? And we can then ask very interesting questions about the scene. And the Deers group, we call it phenomenology. What happens to those photons when they hit the target? And as I said at the beginning, I was a skeptic, I'll be honest. I mean, because it's a cartoon. And the fun thing is we've seen phenomenology in DeerSig before we saw it in real data. Unexplicable or sort of unexplainable type phenomenology that we went back to the LiDAR engineers and said, how's this possible? I said, no, it's not possible. Your instantaneous field of view is too narrow to detect all this multiple scattering events. Yet DeerSig showed us multiple scattering events for a very narrow instantaneous field of view. And then we got data from our collaborators, and lo and behold, we saw the multiple scattering in those real systems. So it's been proven, I would argue, time and time again. So what do? We construct a scene, as you now know, and the version that we used for most of this research, there's now a new version that does a little bit of different ray tracing, but we cast rays into the scene, right? And then we map what happens to those rays at different facets. And you generally develop this kind of photon map that you can map back into the scene as a function of time. And you can see what kind of intensities for the different photon bundles you encountered as a function of time, the x-axis being the time. You can sort of think of the plane flying in this direction and emitting a pulse towards the forest, right? And so we have all this information. We can actually simulate these signals very accurately. And we trust the physics because Scott Brown, Adam Goodenough, Serena, and the other Grady, the other DeerSig team members, they really, that's what they hang their hat on, is actually the physics, and that is accurate, right? So we started with small cartoons because I was a newbie. And I think at that stage, we just didn't have the kind of computing power that we did. I came here to the States working with a team in South Africa in the Kruger National Park. They did a lot of imaging spectroscopy, hyperspectral. They did a lot of discrete LiDAR. And I had to find my role in that team. And coming to the States, working with students like yourselves, I decided waveform LiDAR. No one wanted to touch waveform LiDAR because it's a pretty complex signal, as you'll see. And I got to work with electrical engineers who understand signals, right? And imaging scientists who understand signals and systems. So my first student was a guy called William Wu. And I've used him as an example before. I'll get to him in a little bit. But one of the things, if you look at a waveform signal here on the left, is that you've got this waveform signal propagating through a literal ecosystem, interacting with some foliage, some understory, and then finally hitting the ground in this final pulse. It's often slanted because you're scanning off nadir as you're flying across the scene. But now you have a problem. That signal is actually a product or a convolution, rather, of a bunch of other parameters. It's, if you sort of want to model the waveform, you say my received pulse, this one on the left, is a convolution of my transmitted pulse, which is typically a Gaussian. It varies a little bit, but a Gaussian pulse. The cross-section of the actual target, and then the system's impulse response. When you ask the optech engineers who build the big LiDAR systems in the world, well, how do I get the system's impulse response? They say, well, you take the LiDAR in the lab and you point it at a hard wall and you fire it, and you get that very sharp impulse response to a flat monochromatic type target. So our first departure point was, how do we process these complex signals? And we sort of modeled it in this type of waveform model. And then we tried a bunch of different deconvolution routines, or William did rather. And this is the Richardson-Lucy solution that was the one that actually won the day amongst two others. But essentially sort of iteratively modeling or deconvolving that received response by actually deconvolving the received response from the impulse response and the outgoing pulse. And you've got this sort of termination function that actually compares your received pulse to the iterative deconvolved signal. And you're trying to find that received pulse property and trying to find that minimized difference or residual between that and the deconvolution result. So how did William do this? Because here's the problem. How do I measure or determine the usefulness of any deconvolution routine? In nature, it's almost impossible because I don't know the true cross-section of a tree. It's physically impossible to go measure every leaf's position and angle. It literally is. So he built these little trees. And then he fired lasers at them in deer-sick. And then he could sort of model the deconvolution for different approaches. We used the Richardson-Lucy. This is called the Wiener filter and non-negative least squares. And he used the 2 nanosecond outgoing pulse as the truth signal. So he fired a 2 nanosecond, which doesn't really happen out there. Most folks start at least at 4 nanosecond outgoing pulse. And as you probably know, light travels about a foot in a nanosecond. So 4 nanoseconds it becomes a pretty broad pulse, right? 2 nanoseconds, much better. And he sort of assumed that 2 nanosecond pulse represents the true cross-section of the target. And he used that as the residual term comparison, and then looked at the different solutions. And he said, wait a minute, Richardson-Lucy matches the actual truth signal and the outgoing pulse deconvolved best. And these aren't great graphs, but you're sort of looking at the different, I think the red is the true cross-section, and then the deconvolved is the green. And you can see that we're still not seeing all the detail, for instance, in those two spikes here. Again, intensity by time. Sorry, I should have said that earlier. Intensity by time. So I'm not capturing those two interactions with whatever that might be, maybe 2 branches or so. They're just too close together for me to untangle them. But the Richardson-Lucy came closest. So here we are. We're doing the research in Kruger National Park. Beautiful place to do research, lions and rhinos and everything. And William came up with this sort of, let's call it signal processing chain. First, the denoising, and I'll actually show this. Here's an actual received pulse from the Carnegie Airborne Observatory, a real data set. William has determined that first we want to do sort of frequency domain. We want to find this sort of high frequency noise, smooth it out a little bit. Then this is the outgoing pulse for that received signal on the left here. And this is the impulse response function. And we got that by looking at nadir pulses for Lambertian hard targets in the scene. So basically gravel roads. So this is the hard target response. And this is the deconvolved pulse. So top and bottom are the same 2 pulses. The bottom is just the deconvolved version. And now you can see, hopefully, that there are probably 2 interactions in that pulse, and not just one big convolved interaction. And this is just one example. So here's some example of how William then actually he deconvolved these signals and then voxelized those interactions. So he assigned an intensity per voxel for the scene. And now I can start rebuilding that virtual savanna scene or real savanna scene using waveform data. What do I do with that? We wanted to model things that the ecologists are after. Ecologists are nerdier than we are. You might not believe me, but they really are asking very nerdy questions and very complex questions. So we work with ecologists quite a bit. And you can ask some of the students I've worked with, they really do ask complex questions. So it's up to us as imaging science and the specific imaging scientists in the specific use case to interrogate the data to answer that client's question, I guess. And that's, I think, it's one of the beauties to me of imaging science. You can get a PhD in remote sensing in imaging science. Remote sensing, you're ultimately imaging scientist. You've heard this speech before if you're a first-year grad student. Because William now, he did modeling of grass biomass and woody biomass in Kruger National Park using waveform LiDAR. He's an Apple engineer working on iPads. Never touched remote sensing. He's an imaging scientist. And I think many of the other students I've worked with, and I think the remote sensing folks can corroborate, the optics folks can corroborate, and Gabe can probably corroborate, they don't necessarily go into our specific niche imaging science fields. They become imaging scientists, which is, I think, a pretty cool thing. You're here, so I'm not selling the program to you. I'm just saying, I think it's pretty cool. You should be enjoying this, I think. So here's an example of, on the left, the raw waveform, and on the middle here, the deconvolved waveform. And here's what we saw in that waveform after the deconvolution. We saw that this intensity by time signal, it peaks at the ground. But there's this delayed signal. And William and Joe McGlinchey was doing his master's at that section. Wait a minute. If this is what the grass biomass or the grass component in Kruger National Park, if that's what it looks like, what if this delayed scattering is literally the laser playing around in the grass? So it's multiple scattering back to the detector, and it looks like it's coming from underneath the ground, if you see what I'm saying. Here's the ground peak, and there's something that's beneath the ground, but it's not really beneath the ground. It's just multiple scattering events causing a delayed signal. So what William proposed is he sort of deconvolved and decomposed these into two Gaussians, and then obviously attributed those Gaussians. You can extract a bunch of things from a waveform signal intensity by time, very simple things. You can let your mind wander, but ground thickness, tree heights, and you can maybe take the integral and relate it to biomass, standing biomass that the ecologists are also interested. And he fit a bunch of very simple models. So here's using those Gaussian parameters for the decomposed waveform. You could estimate their herbaceous biomass. Now, I'm not going to write home, but if you're explaining 60% of the variance in a really difficult environment using a single wavelength, single modality approach, it's actually pretty good. So he actually published these results. And he could do other things. He could, height is the easy one. You can see very nice correlation with height. The woody biomass, now it becomes more complex. You think of net primary productivity, carbon sequestration, products such as those. And then foliar biomass, because foliar biomass becomes a very interesting parameter for ecologists, since the foliage is they're the photoreceptors of nature, right? So the better we know how they are distributed, how they're angled, the better the ecologists can populate their climate change models, their carbon sequestration models, things like that. We measure that foliage using a stupid tool like this. So this is specifically an AccuPart. It basically has a string of photoreceptors about a centimeter spaced apart on this rod. And you have one on top of a tower outside the forest logging the incident radiation or radiance, sort of, they call it photosynthetic active radiance, so PAR, so it's visible light. So it just sits there and logs all the available energy. And then Rob and I and others, Amir has done it, you walk around under the forest with an equivalent detector system, and you stand here and you log under the canopy, and you walk around and you log. And it takes the ratio of the logging photoreceptor, if you will, or AccuPAR, and the one under the canopy, and based on some assumptions about the canopy structure, it says leaf area index for that location is 3.5. Nate is laughing, but so leaf area index is the one-sided projected leaf area over area ground. It's unitless. So 3.5 means there's 3.5 square meters of projected leaf area over 1 square meter of ground. And you can see where I'm going with this, hopefully. The higher the leaf area index, the more complex the canopy becomes. So that's one of the key parameters that ecologists are after, leaf area index. And assessing that from imagery, lasers, remote sensing, and other means is a big sort of a holy grail to get that nailed down. So things like foliar biomass becomes very interesting. Then William said, Jan, I've got this job offer from Apple. I have to go and work. I said, who am I to tell you no for, at that stage, I think it was already Tim Cook, I'm not sure. But anyway, off he went, but he still wanted to get his PhD. And I said, William, give me one more paper. What if you can build a tree from our scans? So you get the laser scans and you build a tree. So he did the simulation thing again. He did leaf on versus leaf off simulations. This is a top-down view of each of those scenarios. He applied some morphological filters, which is what you learn, I think, in Carl's class and other computer vision classes. And the goal was to detect the centroid slice in a Z direction and a I direction, so that you can then say, this is the truth geometry of that tree, and here's sort of the centroid slice for that central trunk. Then they used a clustering algorithm called dbScan to look at the point clouds to find the branches. And I know it looks silly, but there's William's reconstructed tree from laser scans, which is pretty cool if you think about it. If you can use lasers from air or space and reconstruct potentially a forest environment. So that's sort of what William did for his final PhD, and or for his final paper, and he came back to defend and got his PhD. So he has a few very, very cool papers. Then things started to happen. Some of you will remember Paul Romanchek, one of the smartest students I've ever worked with, between him and Dave and Calby and William and so on. Paul was tasked to say, okay, if we want to build more complex scenes, how detailed do these scenes need to be for us to accurately represent the physics in the scene for lasers interacting with the leaves? This is a Harvard forest plot. So this is a physical plot measured by, again, the geeky ecologists, where every tree here might be of a different species, oaks, maples, and so on. The heights are accurate, the diameters are accurate, even the leaf year index is accurate for those trees. But for us at that stage, and this is now a good 10 years ago, this was rocket science, this the size of a scene, right? And what Paul did is he could vary the geometry in the scene. He could say, I'm just going to float my leaves, or I'm going to add the trunk, or I'm going to add some first order branches. And now I can compare as I pulse through the scene with those various geometries, either removed or added, how they compare in terms of the signal. And these L's, TBLs, just leaves, trunk, bough, leaves, trunk, bough, first order branching leaves, trunk, bough, you get the idea. So there's all the different geometries as they're added. And long story short, Paul found that he could maintain 95% of the signal by just floating the leaves. And if you remember that graph I showed you right at the beginning, near-infrared laser, highly reflected by foliage, highly transmitted by foliage, very little absorbed by foliage. So it wasn't like it was unexpected, but it was proven. So we could now determine if you just have a trunk, some first order branching with some floating leaves, you can actually represent up to 98% of the scene physics properly. And you reduce the number of facets by an order of magnitude and the simulation run times. So that was sort of the goal at that stage, because computing wasn't where it's at today. So that was all fun, and we published and had a lot of fun. But then the question became, so how do we build better scenes? And I always have this pipe dream of taking a laser like that and putting on a four-wheeler, driving through the forest, because I'm a forest rock long ago, right? And then going back to my forestry office, making a cup of coffee, plugging the hard drive in my computer, and then getting all my statistics for the forest. In forestry, it's also sort of a weird jack of all trades program. You do civil engineering courses, you do silviculture, how to grow tree courses, but you also do a lot of biometry, statistics, a lot, because that's what forestry does a lot, is they do stock taking. So how do I take stock with a laser was ultimately my question. So I've always had a big interest in that system, and that I'll talk to you a little bit later. So we started with the first version of the system that, for the record, I saw during my postdoc time in Belgium. The team there, Dimitri van der Zande was the PhD student, and Paul Couper was the professor. They had a similar system with a 6-sensor laser head. It's a German system that they put on a star-cross railing system in the forest, and they moved it along that rail to scan the forest. But what they came up with is Jason Folring. He was the system engineer here. Some of you still remember Jason very well. I came here and I had my meager startup funds, and I told Jason, can you build a system like this? And he said, yeah, give me 2 months. And Jason came up with this. Now, this to many of you will look like Volkswagen implementation. There's the rusty rotation stage that could collect or rotate the scanner. Everything was wired. Here's an example of Dave Kelby collecting data with this wired system. This was a Pelican case with a physical motherboard and a car battery in the back to drive the whole system. It was pretty clunky, but it worked. It was very robust. So Jason did an amazing job. This sensor that you see here too, I'm not going to do it. Rob wants. We're going to scan the room and show you an example of the data set. But it scans in this plane, so 270 degrees. So only this section at the bottom goes unscanned, and then it rotates 180 degrees. So it gives you a 360 degree by 270 degree scan of the environment. And it's rapid. You'll see it's about 30 seconds in scanning. It's cheap. That sensor head is about $6,000 or $7,000. Francesco Perry is again I think these are computer engineering students, and he saw the system in action in Aardt Forest, and you can probably deduce from his last name is a hot-blooded Italian, and he said, we build Ferraris, you know, we don't like this kind of system that you've shown us here in Aardt Forest. I can do this better. So we teamed up with Crystal Sharp's group and Francesco Perry at UMass Boston, and he came up with that integration where we did the software development and that did the hardware integration, and it became a very, I would say, contained system with a DeWalt battery pack, Arduino system here to run it all, and a very much modern rotation stage. And now we could take that little system, put it in a Pelican case, and it's been traveling across the world. Rob and I have taken it to mangrove forest to do some scanning there, and you'll see in a second. But it's cheap, and it comes at a compromise. So this is a table that shows some of the commercially available systems long ago. This is 2011 table. But you could it's just for comparison, especially if you look at the beam divergence and millirad, it's 15. So it's a pretty wide beam divergence. It has a range of about 80 meters at a 90% reflectivity. And I think it pulses at 33 kilohertz, so 33,000 pulses per second. But it does, and it has a 1/4 degree step angle. So it's a pretty coarse system, but it takes 31 seconds to generate a scan versus some of these systems that take 15 minutes or longer. And that's a no-no when you come from forestry, because you want to scan and move and scan and move and scan and move and go to your office and make the coffee and get the statistics. You don't want to sit there with a generator and have the LiDAR run for 30 minutes and the wind is blowing the trees all over the place. So there's some elegance in that. But this large panel here is actually a commercially available Faro scanner. And just to scale, that's the same scan with our little laser. So you lose a lot of detail. But for our purposes, perfectly fine. But it does come at that cost. You're looking here at a sort of unfolded 3D scan. I think this is an Andreo projection. So on the x-axis, you have this sort of azimuth, and on the y-axis, you have the zenith. So that's why you sort of see the crowns flatten like this. So Dave Kelby, very, very smart student. Roger worked with him quite a bit on the document scanning, so he can attest to that. He's one of these students you just ask him to do something and magic starts to happen. So I asked him, can we start developing this sort of inventory system? And he came up with an approach where you could scan a forest, you could find the ground, find the trunks, the stems, intersect the trunks and the stems with the ground, do that for multiple scan, and then find the overlapping geometries in 2 scan and register the 2 scans. So that's what he came up with, to develop a system like that where you could join 25 scans. This is at 5 meter spacing scan distance, 25 meter scans. And back to DeerSig, what if you could do this? What if you could say, okay, I can develop this or scan this forest scene, But as I said before, because it's a terrestrial system, I have a lot of occlusion on the top of the canopy. So I cannot really sample the canopy all that well with the terrestrial system. But what if you could grow these trees to where they should be if you have some remnant height hits there, and you can populate the trees with leaves based on what you think the leaf area index of that scene should be. So now you have, it's not perfect, but you have a virtual scene based on reality. And that's sort of the ultimate goal. So how did he do it? I give Dave full credit there. Even Bob, I don't know if Bob is here. He was at Dave's PhD defense, and when Dave finished, he said, "What just happened?" It was really good. But Dave came up with this sort of STEM modeling approach where he used a bunch of different algorithms sequentially, but essentially dividing the voxel or the point cloud into sort of different voxels, and then orthogonalizing it, finding this sort of I think he actually used half transforms as well, and then finally ransack to actually fit the lines and detect the stem. So he could actually tell you the stem dimensions up the trunk. And this is extremely valuable in forestry because what you're getting here are taper relationships. And if you have cherry trees, for instance, they're extremely expensive trees. Veneer, if you think veneer and expensive furniture, walnut trees, cherry trees, and so on. When we typically do forest inventory, we measure that what's called the diameter at rest height. I know where it is on my body. It's this little lug-in between my hand with this thing in my breastplate here. That's 1.3 meters above the ground for me, and that's where I measure diameter at rest height. And we measure the height, and we plug it into a model and say, that's the volume of the tree. But what if you could tell a forestry company the exact volume of a tree and the merchantable volume of the tree? So where do the first knots appear in the tree? So you get a very accurate estimation of the value and the extraction that you can expect from any stem. So then Dave did what we just discussed. He took multiple scans. He first found the surface, the ground, and we call it a digital elevation model, intersected that with all the stems that he detected with the ground, find the geometries. Here's just sort of a schematic of that. Scan 1, scan 2, different perspectives, obviously. And we wanted something that's fairly automated. What most commercial systems do is they put polystyrene balls in the scene. They call it tooling balls. So you put 5 polystyrene balls in the scene, and you scan a scene from different perspectives, and you just find the polystyrene balls, and you lock in the scans. But again, practically speaking, can you see a forester with 5 polystyrene balls, a laser scanner, and a 4-wheeler? No. We said, no, we didn't want to do this sort of commercial type approach. We wanted an automated approach. So here's just sort of, again, a schematic. You sort of select a random subset, you fit your models, you find all the inliers, and then you sort of jiggy those 2 scans until those 2 geometries fit as close as possible. And he could even tell you in a 25 by 25 meter scan location with 5 meter space scans, what is the best path to take for least error, how to connect those scans. So you could go from this, find the scans, this is a 2-scan reconstruction, and then you finally end up with a completely meshed scene. So that's what Dave did. And the next generation I owe to Rob Weibel, Air Force officer, PhD, finishing up the semester. Another Air Force officer, Ben Roth, and Grady Saunders, one of the linchpins in a lot of what we've done. So we wanted to develop ever increasingly complex scenes where the physics and the geometries are intact. But one of the questions we had is, what are we actually modeling the scattering of near-infrared light properly in DeerSig? The DeerSig team, they've been very good at doing what's called BRDF, bidirectional reflectance distribution function. I think most of you know what that is. Dr. Bachman works extensively on that with his goniometer. But what about the transmission distribution function? What happens as photons forward scatter, transmit through leaves? Ben was exceptional. He published a bunch of very good papers. He used different species. He used Dr. Bachman's grit, the goniometer. For those of you that don't know, you can place a sample right here in the middle. You can observe the sample and change the illumination geometry. So in an hour or so, you can collect thousands of observation and illumination geometry options or examples. So you can really map out how light reflects off a surface as a function of that kind of viewing geometry. So he did that for a bunch of different species with the sole intent to build better seeds. We had a grand plan in the beginning, but we found that this rabbit hole led us to this. Here at the top are some, call it BRDF examples published from literature. You're looking at the observation angle, sorry, the illumination angle in large degrees, and then the observation angle sort of along the edge there. And then you're also looking at it for visible light. These bottom two are Ben's results, visible light and near-infrared light. And these are just sort of visual comparisons. So first we want to see, do we sort of map to what's been published before? And visually we thought that's pretty good. But then the next thing was, what about the forward scattering assumptions that we're making? And I'm not going to belabor this, but essentially if you used our model derived, so goniometer derived options, they're sort of in blue. If you just assume full light immersion forward and backwards, so in other words, BRDF and BTDF transmission, or then you say, no, I'm going to model reflectance, BRDF, and assume no transmission, and finally model reflectance and immersion transmission. So the takeaway here was essentially, for a near-infrared laser, which is what we primarily occupy ourselves with, we can assume immersion forward scattering distributions, because it's the no reflectance, no model reflectance, no transmission is the only one that deviates from the what do you call it, benchmark, if you will, at different footprint sizes. So this is you essentially varying your instantaneous field of view, your footprint size for the laser from 10 centimeters up to 5 meters. So after all of these wonderful work, Ben worked very hard, we finally said, we can just assume immersion and keep modeling. So Rob Weibel then took over, and he was assigned a hefty task. There's this forest called Harvard Forest. It's in Petersham, Massachusetts. It's extremely well studied from an ecological perspective. Obviously, Harvard operates let's call it the research site, but people from low and far international come there because it's so well studied and measured. And the key thing is, because it's so well studied, we have STEM maps for Aardt Forest, we have inventory data for Aardt Forest. So Rob was tasked with developing a grand scene that we wanted to use for one of our projects. So this is the extent of that grand scene. We call it the mega plot. It's, well, you can see some of the measurement here. NEON, National Ecological Observatory Network. They have a bunch of plots that are extremely well measured here that we could use the data from. Harvard has a bunch of mini plots, different kind of layout that we could also use. There were spectrometer data available, LiDAR data available from a variety of sources from NEON's airborne platform, as well as from NASA. So we could actually validate our scene. And this is what Rob came up with. On the left, you see an actual visual Harvard Forest image. And on the right, you see a DeerSig render of a virtual Harvard scene. Now, granted, they don't look exact, and we acknowledge that, but they're so close that the phenomenology that we cannot really attribute on the left. I cannot physically know all the parameters in this forest, leaf number, leaf angles. You can go to very fine detail. But on the right, I can do whatever I want, and I know the physics. The physics is sound. So how did Rob do this? As we've said before, he used onyx tree. Now, onyx tree is famous for Lord of the Rings string trees. So that's their claim to fame. The Lord of the Rings used onyx tree to build the trees. And he built these trees, a lot of them, more than 100,000 specimens, okay, geolocated across that scene. He parameterized them with the right spectral information. We can program in the payload information. And this is the virtual DeerSig scene. It's about, I think, 600 by 800 meters in extent. On the left here, you see, left column, you see virtual renderings of that scene. And on the right, there's Rob's actual Jeep. You see the real Harvard Forest. And again, if you zoom in, you're going to see cartoonish type look, right, and feel. But the physics is solid on this, so we could actually do a lot of work. This is a sort of sparse area. I believe it's a wetland of sorts, so that's why it looks like it does. So we validated it. On the left, you have actual airborne spectroscopy, measured data. On the right, you have simulated data. So we could cross-compare different species. Again, not perfect, but you can actually, it's less noisy because the atmosphere, we didn't quite put all the atmosphere that you would see in a real scene on the left. And now we can use it. And I want to sort of have you think about, think outside the box. You have a scene that you can toggle switches left and right. Think of the usefulness for generating huge data sets for artificial intelligence, machine learning, things like that. So Yuval is working with Rob and so on, where we can take this virtual scene. We have absolute truth. We know what's in every voxel to the hill. We know exactly what's in every voxel, right? So we have absolute truth about the scene. We can simulate based on the physics, the laser interaction, voxelize the laser, and now we can do classification. What if you can tell what is underneath the canopy by training a machine learning a classifier, by putting tanks under the canopy, by putting Humvees on the canopy, by putting buildings on the canopy, by putting deer path under the canopy, and you can actually train that classifier to detect just based on laser scans because you actually had access to absolute truth. So Yuval is working with Bartek in the back there. We've had some heavy hitter AI folks now in the house. So I could say Yuval now has the support he needs on that front. So Yuval is developing these. I'm not going to read all of this. You can read it yourself. I don't always know what's going on with machine learning, and I'm not going to claim that I do. But he's developing these neural networks that can actually take as input the truth data that we can generate in DRC, and then use the signals we generate from the laser and classify, detect those truth data sets. Amir is also working on this. Yuval is doing voxel classification. Amir did more of voxel quantification, if you will. What amount of material can you find in each voxel? And here's just some of Yuval's very early results. And it's pretty simple at this stage. It's evolved quite a bit since then. But you can see him classifying the foliage, the trunks. And again, this is a single modality, single wavelength system. So you don't have the benefit of spectral power, right? And then objects. And he had very good accuracies. Bark, not so good because it's also highly reflective in the infrared. So there is confusion between bark and leaves, for instance. But objects, you can actually get pretty decent object detection. And we keep working on this. Keith Krause from Neon, he can now also model what is the occlusion in a laser data set. Here's a single flight line at the top. So all the black occluded voxels, I cannot see what's in them because something else is opaque before the laser got to that voxel, right? And if we just combine 3 flight lines, you can actually map all of the hidden spots in the forest. And there's a lot of useful information for whatever purpose. If you think you're an ecologist and you're extracting biophysical parameters of a forest, it's great to know what kind of validity you can attach to those biophysical parameters because you didn't scan properly. And if you want to know what is underneath the forest for any purpose, it's good to know which voxels did I not scan and which voxels are truly empty. You know, so there's a lot of use in that. This is transmission, so same type of deal where you sort of see the sort of brighter colored voxels are highly transmissive, and the sort of orange voxels are opaque. So you can actually map where your obstructing features are in the signal for that. And then finally, and I'm not going to spend too much time, I have to wrap up, but Kedar, you might not believe it, but again, there's a lot of interest in leaves. So one of the questions is, how does leaf angle distributions impact the assessment of forests? So different species have different leaf angle distributions. Literally, you can walk in the forest and you'll see it, right? They're not all. So you can tell me rectophile is like this. Where's Kedar? Is there some? Rectophile and planophile and anything in between. So Yuval can look at different leaf angle distributions and embed them in DRSig and simulate and say, if you wanted to assess this parameter as an ecologist, this is what you have to be careful with, or for what you have to look out for, that could be influenced by different leaf angle distributions. So he's doing research on that, and he's hoping to graduate this year as well with his PhD. And there's final 2 slides here. What's next? I just grabbed these off of the DRSig presentation. This is what Serena and Jacob and others in the DeerSig team have been up to. They're building this amazing, I think you call it the Alpine scene, right? Where they're building hundreds of kilometers across scene that could be used for simulation purposes. So it's really growing by leaps and bounds. And we live in an interesting age where, how can I say, you're not wowed anymore because you watch Avengers movies, right? And Thor does amazing things flying through the air. But think of it from a just, I almost want to say, visible range perspective. It's pretty easy to do a very realistic rendering in the visible range, I think, these days. Maybe I'm dismissing Jim's work, but you know what I'm saying. You look at some movies and you could almost not distinguish reality from virtual. But it becomes pretty complex to make sure that a scene like this stays true to its nature across the reflective domain, the microwave domain, etc. So they're building these huge scenes that can now be used for science. So you can lie unless you don't. And we've actually found that Wei Yao, another student of mine, he collected leaf area index out in the Sierra Nevadas, and we got pretty poor results for what he collected in the physical scene to what we modeled from an airborne system. Then he modeled this thing in DeerSig in a virtual scene, and he came up with a collection protocol for this in the real field. We went back the next year. He followed his virtually developed protocol, and our real models improved significantly. And so that to me, things like that to me really proved out the method, if you will. So, I'm going to stop there and sort of hopefully you got an idea of what a lot of these students have been up to with DeerSig and lasers. And I've asked Rob to scan the crowd so you can see what you look like in our little lasers world. So I don't know if you can share, Rob, or not. Yeah. Or maybe not. I don't know. So this is the scan from that laser, and you see it's sort of colorized by, I think, intensity, right?
This is just height.
That's just height.
That is high. Take off the ceiling.
Yeah, there I am somewhere there. So it's about 1 million points for a room this size. So it's not in that sense impressive. The more commercial sensors that cost $250,000 will give you probably between 30 to 80 million points, depending on the scan setting. This system right here costs integrated about 15,000, but it scans in 30 seconds. So it's extremely useful in that sense. So, but yeah, I'll stop there. I don't know if you have any questions. Yeah, that's the embryo projection of the crowd. So
no, great talk. Thank you. The question just about weather. So I guess you probably wait for it to be beautiful and a nice day for a hike before taking your measurements, but maybe that's not like the right assumption to make about certain forests where it rains a lot. What kind of assumptions you make and how do you time your measurements around weather?
I think in the spectral domain, it's more critical. So when we do, you can talk to John. He's a imaging spectroscopist, but we typically time our collects. You're right, when it's a sunny day, and we call it between plus minus 2 hours of solar noon. Then we're sort of hoping for a nice, BRDF type properties. And then folks like Emmett, who's in the back of the room, they're working on calibration options where we needn't wait for perfect sunny days, because if you think about some of the applications, a farmer cannot wait for a perfect sunny day to scan the crops or to fly the drone. So he or she needs to collect data, even if it's cloudy, because the cows need to be milked now, and the drone, you only have half an hour to collect the flight, right? So we are working with, Carl has done some calibration experiments too, where you're using in situ onboard downwelling sensors to collect the inbound radiance, and you just use that and the upwelling radiance to convert to reflectance in real time, which is a very effective method. And he's shown with Babak, one of his students, that you actually get very close to the gold standards with that. For lasers, we're less influenced more by wind, ironically, because there is some dropout in the lasers when it rains really hard, but not much. It has to rain really hard. But the wind actually impacts us a lot because you can imagine as it's scanning and it's doing its rotation and the trees are doing this. So yeah, that is tricky.
Bizarre one in my I noticed your Harvard forest there. It was right on the track of the 1938 hurricane. And there are forensic foresters who go out in New England and they find traces of trees that fell down in the hurricane. And I was wondering if that's, I assume that's something you could do with this system. And it actually might be kind of interesting to try.
Yeah.
If you're not doing it already.
Mike McClelland, another Air Force officer, he actually used drone LiDAR data to map disturbances like that. And it was funded by, of all people, by Staples. Staples wanted to source their paper from sustainable growers. So the non-sustainable way to grow a forest is you buy a piece of property, you harvest everything, you sell the timber, and you sell the property for whatever use, right? So Staples wanted to be sure that there's some auditable ways to actually look at that someone do something like that, or that they do selective logging, more sustainable. So you can absolutely do that, Roger. So Mike developed ways to classify natural and non-natural disturbances and characterize the forest that way. Because you can, to a large extent, see through the forest. That was so much.
How does DeerSig simulate color? Is it already baked into the 3D models? Or?
I have to ask the DeerSig folks, but essentially, the way I understand it, if you measure this chair, you also have to actually collect a spectral sample of all the facets, not all the facets, all the materials of the chair, and ideally the BRDF of each of those materials, so that then when you render it, you will render it in true color or in true spectral or laser world. So the long story, you bake it into it by measuring it and then parameterizing the model properly. Yeah. Other questions? Well, thank you very much. Next week is Dr. Craig Glennie from University of Houston. He does a lot of real laser work. And so I think it's going to be a very interesting talk. He's a very interesting guy and he works a lot with NGA on laser research. So I hope most of you can also attend next week's talk. So, thank you.